Hello, my name is Stephen Van Pelt, and I am here today to present challenges in fabricating capillary-driven cold plates used in hybrid two-phase cooling systems. I know that is a very long and verbose title, so hopefully throughout the talk I can actually break down what some of that means and give you a better idea of how we're rolling on this. So let's move into it. So firstly, I just want to throw out an acknowledgement to my other two authors on this paper, who are very valuable throughout all of this. The first being Dr. Mohammed Reza Shari, who's a senior research and development engineer at ACT. He was kind of the driving brains behind this and it was his brainchild. And I was lucky enough to be able to work with him and kind of work on this project and really get some cool results. The other person I would like to thank is Max Demidovich. He was the lead technician. He was kind of, it fell upon him to make sure that everything ran smoothly technically, and he was able to get everything together from the testing cart to the actual cold plate itself. So as I said before, I'm Stephen Van Pelt. I am a research and development intern with ACT. And I was lucky enough to actually get to work on this project with them and get to work on this paper with them and get to see the cool results that came out of it. So with all of that out of the way, let's get into the fun stuff. So first, let's actually take a look at this capillary-driven cold plate. First, I just want to break down what the capillary-driven part is. So within this cold plate, there are actually wicks. So there are wicks and a non-permeable barrier, which I will show a little bit later in a little bit more depth. But basically, they serve to let there be a capillary drive from the liquid region containing refrigerant to a vapor region, which allows for a very quick removal of heat through these heaters. So taking a look at this picture, I want to just point out some of the major important design points that we actually looked at in this cold plate. So you'll see that there are 4 heater blocks. Each has a wick placed below it. And then you'll also see that there's 1 inlet and 2 outlets. So we have an inlet for the refrigerant, the liquid inlet, and the liquid outlet, and then we also have the vapor outlet. So for this testing, we used R245 FA. There was just one we had worked with in the past and one we chose for this one because we know the thermal properties of it. So you'll also see that within this design, we also have 2 steel plates designed to keep the cold plate pinched together so that everything stays in place throughout testing. So this is kind of the outside look. So let's look more towards the inside and let's look at this blown up view. So as I mentioned before, one of the very important things that makes this capillary driven is this NPB. So you'll see here that that is this black rubber, which is right in the middle of the picture. So this NPB is specifically designed that it seals the wicks in such a way where there is a little bit sticking out in this liquid region in the outside, and the central part is actually within the vapor region. So what this does for the cold plate is it allows that as there is heat input through the pedestal, the refrigerant that is within the wick can boil and escape through the vapor exit, and through capillary drive, it can actually pull more of the refrigerant in from the liquid, and it can continue this process. So it's a continuous process that where it just keeps boiling, and it allows for a lot of heat dissipation if it is working well. Um, so a large part of this is actually the NPB, and it is one of the most vital parts of the actual design. So, speaking about that, let's move to the other most vital part, which is the wicks. So in our setup, what you're looking at here is that top plate that had the heater blocks on it. If you just rotated and looked at the bottom, as I said before, there were wicks that were placed under each of these heater blocks, and they were laid out in this orientation. So we chose square wicks, each 3.5 centimeters by 3.5 centimeters, and each is 5 millimeters thick. So this is what's actually doing the wicking. This is what's allowing the transport of the liquid refrigerant through to be boiled via the heat from the heating blocks and then to be escaping as vapor. And it's what's allowing this heat transfer. So mentioning the heating blocks, those were also specially designed. So here you can see a close-up of the actual heating block. So you'll notice there are a couple different size holes through this, and each plays a very important role. So the large block at the top with the 2 holes was actually slots for cartridge heaters. So that's how we provided heat throughout this process. and throughout our testing was we had 2 cartridge heaters that went into each heat block that we can control how much the heat was actually going through. You'll also notice that there are 3 holes in the bottom in the actual pedestal. Those are so that we could put in T-type thermocouples so that we could measure the heat across the block and get an average heat that was traveling down through this pedestal, which comes up in calculations. So with the actual cold plate described, let's move on to the testing apparatus and the experiment loop itself. So here we have the experiment loop, and there are a number of important features in this, but I like to start at the cold plate and just kind of move through as the refrigerant would. So starting down here in the bottom right at the cold plate, you'll see there are 2 outlets as I've described. There's a liquid outlet and a vapor outlet. Both have pressure and temperature sensors on them, so that we can measure those at both outlets to analyze how those are working. So you'll see that the liquid outlet very simply just goes around, comes through and drops into a reservoir, which is just a big storage tank for us so that we can run this very continuously. We don't have to worry about like too little refrigerant in the lines. Then you'll notice that from the vapor outlet, it actually goes through what we label here as a heat exchanger, but it's just a chiller. So it's just to change the vapor back to liquid so that it can be stored in the reservoir. So once it's in the reservoir, it's ready to be called upon, and we can just pull it through this system, pull it down, pump it up to whatever pressure we need, and then it goes through this preheater. So this preheater is a very important part of the design because it allows us to control the inlet temperature at the cold plate. So for our testing, we maintained it from 13.2 to 13.8 degrees C. But the inlet temperature is very important because that's what it's allowing us to control the degree of subcooling, which is very important in any refrigerant testing and any evaporator testing. So that was our main experiment loop. We actually built this out on a cart that had a large amount of electronics through it. So most of it was controlled through transformers that were in the actual cart. And then we could mount different heater, we could mount the cold plate on the top, and it had interchangeable valves and kinetics so that we could actually just take one cold plate off, put another cold plate on, and all working in this one on this one card. So with those 2 established, the way we were looking at data collection is we wanted to look at 2 main things. So we wanted to look at the heat flux and the thermal resistance. So there was kind of some background thinking before we could get to those, and that's how I'm going to walk you through it. So firstly, we knew from single phase testing that the electrical input heat is absorbed at about a factor of 0.84 degrees. And another thing we know is that the area of the heater is 2.33 centimeters squared, which is just something that pulled from the design. So once we take these and known equations, we can actually very easily get to those 2 equations we want, the heat flux and thermal resistance, and we can define them for each heater. So we define them here. So you'll see the top equation is the heat flux for a given heater I. So that 8.4 factor comes into play in that. The top is the electrical input for the heater I, and then the bottom is the area, which is why that 2.33 is valuable. And then if you look at the bottom, the thermal resistance for the heater I is the temperature at the surface of heater I minus the temperature in plus temperature out all over 2, all of that divided by the heat flux for that heater. So those were the 2 major values that we looked at and what we were basing all of our testing on. So with that, we were then actually able to gather data all through a DAC system. So we had all the thermocouples run into a DAC, and we could actually plot it in real time. And we were actually able to then take all those temperatures, put them in here, all the electrical inputs, and we were able to come up with these 2 plots. So these are a plot of heat flux versus the thermal resistance for the heaters. On the leftmost graph, you'll see that it's actually for 0.5 liters per minute, and on the rightmost graph, it's for 1 liter per minute. And then you'll notice that the different colored dots just correspond to the different heaters along the cold plate itself. So you'll notice that on the left, we have they stay very linear across. And on the right, we actually have a slight tilt up, and then it levels out. So analyzing this, we were thinking, what conclusions can we draw from this? So firstly, we were originally only planning on running at 0.5 liters per minute. But what we realized was that the single phase heat transfer had significant effects inside the cold plate. So we actually had to increase the flow rate and run it at a higher flow rate as well. So that's why we ran that 1 liter per minute. But even in analysis of that, we were realizing that they were still showing poor thermal performance. So when you're looking at the cold plate, as you increase the heat load, you should actually see your thermal resistance decrease. However, we actually observed a leveling off and then the opposite. So we had to sit and think and go, all right, well, what could have caused this? So we know that one of the most major problems that can happen in a wick is flooding. So flooding means that the NPB seal is broken and all of the refrigerant get in, your wick floods, or you dry it out if you break the seal the wrong way. So that all hinges on the NPB seal must be perfect. So we decided to actually take a look into this. So after we ran these tests, we looked in it and we pulled out this actual picture here. This is a picture of the actual heater that was run, and we observed a significant blowout on the fourth heater. So you can see that if you look to the far right here, the fourth heater had this blowout that was caused by the seal not being lined up properly and not actually like lined up precisely. It caused this blowout. The vapor blew it out and then it covered the whole wick. So our whole fourth wick wasn't heating. But what that also did was it broke the seal and it allowed for the flooding of other wicks. So basically both wicks were flooded and we were at the critical heat temperature. So right away, we were achieving poor results, which is what actually leads us into our thinking about this and the drawbacks that come with this in hybrid two-phase systems. Specifically, this design is that it demonstrates the complexity that comes with manufacturing this cold plate. We looked in and we triple checked out and we thought that we had it lined up perfectly, but we were off by a fraction of a millimeter and it allowed it to blow out. And that's one of the big problems with this, is that they are very complex and they require this extreme precision, which if you mess up just slightly can cause major issues, as we saw in this testing. So we see this as something where it's certainly a learning point, because now we can look towards the future and go, all right, well, how can we pivot off this and how can we learn? And what we see as the future in this is actually there are many challenges that come with this, specifically flooding, but we think we found a way to actually get around that, which is additive manufacturing. So via additive manufacturing, we are actually able to circumvent the problem of this NPB being placed improperly while still actually gaining all of the increased thermal properties from wick evaporators. And we've already started investigating this. So additive manufacturing or 3D printing basically lets us get around this, because we don't have to worry about the NPB ever moving, because we print it in place and it is locked in place. So we see additive manufacturing as a streamline for the process that will allow us to reduce the complexity, expenses, and time required for the manufacturing of these cold plates. So with that being said, I want to thank you all and ask if you have any questions.